So now we are going to discuss low power design in VLSI at the circuit level. So first let us see the introduction part, the power consumption in circuits. The power reduction techniques at the circuit level are quite limited if compared with the other techniques at higher abstraction levels like gate level, architecture level, algorithmic level, behavior level, and software level. At the circuit level, percentage power reduction in terms is considered good. However, circuit techniques can have major impact because some circuits, especially in cell-based design, are repeated thousands of times on chip. Therefore, circuit techniques with a small percentage improvement should not be overlooked. Circuits designed manually can often be analyzed in great details. This allows us to optimize the circuit speed, power, and area to suit our specification. One important circuit technique is the reduction of operating voltage. The general rule is to select the lowest voltage that is acceptable. The main thing power reduction in circuit level is transistor sizing and gate sizing. At the circuit level, transistors are the basic building blocks, and a digital circuit can be viewed as a network of transistors with some additional parasitic elements such as capacitors and resistors. Transistor sizes are the most important factor affecting the quality, that is area, and power dissipation of a circuit. Some studies assume that the sizing problem is a convex function and linear programming can be used to solve the sizing problem optimally. Another problem encountered in cell-based design is gate sizing. The goal is to choose a set of gate sizes that best fits the design constraints. First, we will see transistor sizing for leakage power reduction. An interesting problem occurs when the sizing goal is to reduce the leakage power of a circuit. The leakage current of a transistor increases with the decreasing threshold voltage and channel length. In general, a lower threshold or shorter channel transistor can provide more saturation current and thus offers a faster transistor. The presence a trade-off between leakage power and delay. The leakage power of a digital circuit depends on the logic state of a circuit. Consider a simple two-transistor inverter. If the output of the inverter is logic 1, that is high, the leakage current of the inverter is determined by the N transistor that is turned off. Look at the diagram. The transistor sizing relevant to the leakage power reduction is given here. If you see the first structure, this is N, this is P mass, this is N mass. This is width of the transistor P, length of the transistor P, 20 divided by 1. This is width of the NMOS transistor, length 10 by N. So the rise timing is 1, fall timing is 1, the leakage power is 1. Okay, to reduce the leakage power, you come to the second structure. This is the stage probability. So the state probability remains the same. Only we are going to change the width and length of the transistor. Here the PMOS transistor won't change. The length and width of the NMOS transistor is changed. This is 1 replaced by 2. What will happen? The rise time remains changed once the fall time is changed by 2. The leakage current is reduced very low from 1 to 0.1. The third diagram, there is no change in NMOS transistor because there is a change in the PMOS. the length of the PMOS is changed 1 to 0.5. You look at this one, there is a no change in the leakage current. So whenever there is a input is 0, output is 1, at the time we have to change depending upon the output. The type of transistor length or width will change to reduce the leakage current. So the output is low, the leakage current depends on the P transistor. In order to suppress the leakage current, we can increase the threshold voltage or the channel length of the N transistor. So however, by doing so, we also increase the delay of the inverter because the N transistor now offers less saturation current when it is turned on. If we are fortunate that the falling transition of the inverter is not the critical delay, we can use skewed transistor sizing method to reduce the leakage power without incurring any delay penalty.